Okay, 2.2 is the first section of the course. In this section, it's really a review section. So looking at some different things in terms of graphs and mostly graphs of functions specifically. So the first example here is looking at graphing, and this guy's called a piecewise defined function because this guy's defined in 3 different pieces depending on the value of x that's chosen or that's input into the function. So my goal is ultimately to graph, but I guess, I could do some other things as well while we're here. What if I just do some evaluating? Like, what if I say, let me plug in the value 5. So that means the x is 5, determine what the y is. So the first thing I have to do is I have to look at these sets and I have to decide which of those sets the x value 5 falls into. Okay, 5 is not less than -1. It's not between -1 and 2. It is greater than or equal to 2. Okay, so that means this is the piece that I'm going to plug that value 5 into. Okay. So the result is -10. Okay, so what did I find? Well, I actually found a point on the graph. That would indicate that the point 5, -10 is a point on the graph of this piecewise function. I can keep on doing this. So what if I plug in, 1? Okay, so first I have to look and see which set 1 falls into. Well, 1 is in between -1 and 2. So that means I would plug 1 into that middle piece. So what have I found there? I have actually found another point on the graph of the function. I could do as many of these as I want. I'll do one more. -3. Okay, -3 is less than -1. So that top piece is the easy piece. No matter what value I plug in for x, I just get the constant -3. Okay, so what have I actually found? I found 1, 2, 3 points on the graph of the function. But, if I was just to plot these 3 points, I can do that. 1, 2, 3, 4, 5, 2, 4, 6, 8. Okay, here's this point down here. 5, -10. Here's 1, 2. -3, -3. Okay, well, that's fine enough, but that's really not all that helpful in terms of actually graphing the function. Okay, so what's another idea? So another thought would be, well, actually, I know what each of these 3 pieces looks like. These are recognizable functions. So here's what I like to do kind of as a first step. I like to look at these domains here on the right, and I like to say, well, where does the graph break from one piece to the next? So you see how at x equals -1, I move from this piece to this piece? So here's what I'm going to do. I'm going to put a reference line at x equals -1. So I'm just dashing in here. This is where I'm going to jump from the top piece to the middle piece. Okay, what is the next spot where I'm going to have a jump? From 2, at 2 I jump from here to here. Okay, so the next reference line would be here at x equals 2. So that's just to help me kind of set this up so I can see where the graphs break, okay? All right, now let me look at the pieces. So to the left of x is -1, I'm going to be graphing y equals -3. in between -1 and 2, I'm going to be graphing x squared plus 1. And to the right of 2, I'm going to be graphing y as -2x. So that kind of gives me a starting place. Then I've got to remember what each of these shapes look like. So something like y equals -3. That's a special one. That's just a constant function. That's a horizontal line, isn't it? That's really easy to graph. I go to y equals -3 and I draw a horizontal line. Okay, what about the endpoint? Because I have to decide here, does this endpoint stay an open circle or does it get shaded in? So to decide that, what I'm going to look at is the inequality here. So you see how this is a strictly less than? So that means it does not include the endpoint. So that circle there is going to stay open. Okay, so something like that. All right, now let me graph y equals x squared plus 1. I recognize that one. X squared is a parabola. That one's shifted up 1. So even if I just plug a few values in there, so what if I start with the value on the left? So x is -1. So y would be -1 squared plus 1 would be 2. Okay, let me plot that point. It's here. I'm going to leave this open for the moment. We'll look at the ends when we're finished filling in this portion. Now let me plug in some other values in that region. So I plugged in -1. Let me plug in 0. That's 1. Okay, I already plugged in 1. Let me go ahead and plug in 2. So 2 squared plus 1 is 5. Okay, so again, for now, I'm leaving the ends open. Once I draw in this parabola, then I'm going to go and look at the endpoints up here. Okay, this guy is closed. Okay, so that means I have to go and close this point. Okay, so that guy's closed. Fill that in. Versus 2 is open. Okay, so that means this one here stays open. Okay, all that's left, graph my y equals -2x. So that is just a line, right? The slope is -2. The y-intercept is 0. So I mean, I could graph that using the slope and the y-intercept. Or another idea is, well, I could just plug in points, connect them with a line. So that seems like that might be kind of more direct. So this is true, but I'm thinking, let me just plug in some points. So I'm graphing on this side, right? So I'd start with 2, and then I plug in 2 and bigger values. Okay, so I'll plug in 2. Y equals -2 times 2 is -4. Leave the end open for now, and then we'll decide. Plug in one more even. 3. -6. Okay, and then I connect these with a line. Okay, now let me go back and look at the end. This guy is inclusive. That one will be closed. So I need to close that in. Okay, so then I have a graph. So the only thing left to do from there would be clean the graph up a bit. Seems like good idea. So I have these reference lines. These were not really part of the graph. We really just use those to help us fill the graph in. So I think at the end here I would go ahead and delete those. Okay, clean some of this up. Okay, and there's my nice complete graph. And so you can see these points that we found earlier. These do lie on the graph. But I mean, in and of themselves, I mean, on their own, they're not really all that useful as far as actually graphing the function. Okay, so what else can I do? Let me do maybe one more thing with this one. Let me list the domain and the range. So the domain, so I'm going to look at the graph and I'm listing all x values that are achieved. So I have a couple of different notations for how I do this, but let me start by just looking at the graph. Okay, so I'm starting on the far left and I'm moving to the right. Okay, so I'm starting to have everything from negative infinity up to -1. Then I jump up here, but I mean that x value -1 is still achieved. Then I move over to x equals 2. Again, I jump down here, but that x value 2 is still achieved, and then all the way over to infinity. So to me, looks like I have two options. I can write negative infinity to infinity. This is called interval notation. Or I can write the set of all the x's where x belongs to the set of real numbers. This is called set builder notation. Okay, so how do I read this again? The set of all the x's where x belongs to the set of real numbers. So maybe I can, let's just clean some of this space up. Kind of go through that one more time. So when I write that, I write the set of all the, and then I put the variable. And then in this vertical line says where, or such that. And then I write whatever the condition is. That's kind of the template for that set builder notation. So when I wrote this one down here, what I wrote is I wrote the set of all the, and then the variable that I'm interested in with domain is x. And then I said where, such that x, this means belongs to. So x belongs to the set of real numbers. So I use R for real numbers, and then the double line here makes it a set. So this just says x belongs to the set of real numbers. Okay, let's do the range as well. So the range I'm interested in, the y values. Same idea. Okay, so let me start on the graph. So I'm starting the lowest this graph goes, negative infinity. Okay, then I go up to, I stop here. Now here there's actually a jump between here and here. So let me see if I can write this out. So I have negative infinity up to, what is this here? 1, 2, 3, negative 4. Bracket, because that value is included. Then I say union. So this is the mathematical way of saying or. Okay, so I say union, then I list the next value. So again, here on the graph, the next value of y is just this single value. So we have a special way of indicating just the single value there. And the way we do that is we use these curly braces. So that value of y is negative 3. And then I say union again, because then I jump up to here. Okay, and then I have the set from here to here. So what are those values? 1 included, but 5 is open. 5 is not actually achieved. So there's my range. Okay, so my range, let's see which notations we're looking at. So that is the interval notation. It's the one where I'm using brackets and parentheses. Now I'm going to write the set notation. Set notation, I'm using this template. Okay, so I'm going to say the set of all the, okay, I'm talking about y now. And then I want to list these inequalities. So y is either less than or equal to negative 4, y is equal to negative 3, or y is in between 1 and 5. So there's my set builder notation. Okay, so should I go in and highlight these? Let's see. So there's my range and interval notation, set notation. Here's my domain, interval notation, set notation. Right, so that's a little review on graphing piecewise defined functions. Here's the next thing. So the next thing is kind of some terminology, some little definitions that you'll remember from algebra. So first of all, I have this series of graphs. First question is each graph a function? So maybe let me see if I can move this down a tiny bit. A little more space there. Okay, so is each graph a function? So do you remember how we answered that? So for a relation to be a function, each x has to have only one y, and we could check that graphically using what was called the vertical line test. So I'm going to start by just going through these graphs, and I'm going to check if each is a function. Should I number these? Okay, number 1. So if I pick a vertical line, any vertical line, and I draw that vertical line through the graph of the function, you can see it crosses only one time. In other words, each x has only one y. So this guy is yes to function. So should I put just an F here for function? Okay, next one. Any vertical line I choose crosses the graph only once. This is yes to function. Number 3, however, if I choose a vertical line here, you see how that one x has two y's. This is not a function. Number 4, same idea. If I pick an x here, that line crosses twice. This is not a function. And one more, again, does not pass the vertical line test, not a function. Okay, so that part's really easy. So what else does this ask here? Okay, then it says, if so if it is a function, is it then also a one-to-one function? Okay, what does that mean? That means for each x, there's only one y, and for each y, there's also only one x. In other words, not only does this pass the vertical line test, the graph would also have to pass the horizontal line test. So there would be a one-to-one correspondence between x and y. Okay, so remember, one-to-one, we only use that term to classify functions. So when I'm looking at the graphs then, I actually would only apply that term if I'm already dealing with a function. So only really graphs 1 and 2 would be classified as one-to-one or not. So if I look at graph 1, let's clean up graph 2 here while we're at it. So look at graph 1. It was a function. Is it a one-to-one function? No. This y value has more than one x value. So it's a function, it's not one-to-one. Something like number 2 though, any horizontal line I choose crosses only once. So this is a one-to-one function as well. And I don't classify the others because I'm only classifying functions as one-to-one or not. Okay, so then what else is there? Okay. Any symmetry, okay? Clean these up a little bit again. Okay, so symmetry. That means like a mirror image, the same on both sides. So in this class, we only look at 3 types of symmetry. Symmetry over the x-axis, the y-axis, and the origin. So if you look at this first graph, if I was to take this graph and I was to cut it here, in other words, I was just to cut this side, and then I was to take that and I was to say, fold the graph over the y-axis. If I fold over that axis, this piece here would land here, okay? So this first graph is symmetric over the y-axis because when I fold over the y-axis, I have a mirror image. Okay, let's see. What about number 2? Well, number 2 is an interesting one. Because if I was to take that graph and just fold it, say, over the y-axis, well, here's what would happen, huh? This would be the graph I would end up with. Well, that's not exactly the same. Okay, say I was to take the graph and I was to fold it over the x-axis. Okay, then here's the graph I would end up with. Oh, same thing. Okay, so this guy's not symmetric over the y-axis or the x-axis. However, there's one other type of symmetry we look at, which is symmetry over the origin. So that means we would fold twice. Okay, so this is a little harder to visualize. So I would take the graph, I would pick an axis, doesn't matter which one. Say I pick the y-axis. I fold the graph over the y-axis. Here's what I get, right? Now I'm going to take that and I'm going to fold it over the other axis. so over the x-axis. So if I take that now and I fold it over the x-axis, indeed, I get back the original graph. So in this case, I'm folding twice. So once over either the x or y axis and then over the other. If I get back the original graph, in that case, I say the graph is symmetric over the origin. Okay, now we can still classify the other graphs here as far as symmetry, even though they're not functions. Okay, a circle is nice because if I take that, fold it over the y-axis, this piece lands here, so it's symmetric over the y-axis. What if I fold it over the x-axis? Then this piece lands here. Okay, symmetric over the x-axis. What if I fold first over, say, the x-axis? This lands here. Then I fold over the y-axis. Then this piece lands here. No matter how I fold that, I arrive back at the same circle, right? Circles are special. So this guy is symmetric over the x, y-axis, and origin. So all three. Over the x-axis, the y-axis, and the origin. Okay, what about number 4? It's not a function, but regardless. So let's see. If I fold that over the y-axis, then this lands here, this lands here. Okay, so it is symmetric over the y-axis. Let's see if there's anything else. Okay, what about the x-axis? Not quite, because if I take this and fold it down, it lands here. Okay, so that doesn't quite work. So then that wouldn't be symmetric with the origin either. Okay, so this one just symmetric over the y-axis. What about 5? Well, 5, if I fold over the x-axis, this lands here. Okay, so this guy is a graph that's symmetric over the x-axis. Okay, anything left to answer? One more set of terms, even and odd functions. Okay, so for functions, we like to classify those as being either even, odd, or neither. We kind of write a little explanation of that up here. So again, these terms only apply to functions. Otherwise, we don't classify. Okay, so if you look at number 1, number 1 here is an example. This is a function. This is an example of a function that is called an even function. It's symmetric over the y-axis. Okay, this guy lands here. So we call number 1, call this an even function. Okay, so what does that mean? That means I have a function whose graph is symmetric over the y-axis. Okay, so there's only one other term here. That's an odd function, but we talked about 2 other types of symmetry. We talked about symmetry over the origin, we talked about symmetry over the x-axis. So which one is an odd function? It must be one that's symmetric over, well, is it going to be the x-axis or the origin? Okay, here's the thing. Remember, these terms only apply to functions. So look, here's a graph that's symmetric over the x-axis. It would not be possible for this to be a function, would it? Because then it would not pass the vertical line test. So it must be that an odd function is a function whose graph is symmetric over the origin. So that would be something like number 2 here. Okay? So we would call number 2 an odd function, symmetric over the origin. Now the others are non-functions, so I wouldn't actually apply those terms to any of the others here. Okay, so the next question would be, what if I'm given an equation? So you see how here I have a series of equations. And what I want to be able to do with these equations is I want to be able to determine if each of these functions is even, odd, or neither, but I'd like to be able to do that without actually graphing each of those functions. Okay, so the idea is, can I come up with a test that I can use to check algebraically if a function is even, odd, or neither? So I started with kind of just a couple generic graphs. Okay, so here's a function, generic function, that's like an even function. Okay, maybe something like that. I didn't do a great job graphing it, but its graph is symmetric over the y-axis. Okay, so here if I pick a generic point, x, y, okay, because this is an even function, because this graph is symmetric over the y-axis, I know that the corresponding point on the left side, the x would be negative, the y would be positive. Okay, so wouldn't it be true then that if I plug negative x in the function, I get the same y value as if I plug positive x in the function? That's just the algebraic way of saying if I plug positive x in or negative x in, the y value that I get out is the same, right? Let me do a generic graph of an odd function. Okay, something like that maybe. So if I pick up xy point there, for an odd function, this graph is symmetric over the origin. So that means I'd flip once and flip again. So here, the corresponding point would be negative x, negative y. So in this case, if I plug negative x in the function, I don't get the same y as if I plug positive x in, I get the negative of it. So this is just saying, if I plug positive x in, I get positive y. But if I plug negative x in, I get the opposite of y, I get negative y. So actually I can use these as tests to determine if a function is even, odd, or neither. So here's the first example. And I'd like to use these tests, okay? So here's what I do. So step one, plug in negative x. So I find, let's do this in black, find f of negative x. Okay, so I have an odd exponent, so that would stay negative. Okay, then step two is to compare. So I'm really looking at two things. I'm saying is let's say it this way. Say even, odd, okay, so for the function to be even, f of negative x has to be the same as f of x. Okay, so here's my f of negative x. So we're saying is f of negative x equal to f of x. Are those two things equal? No, those are not equal. So I would conclude this guy is not even. What about odd? So for the function to be odd, f of negative x has to be negative f of x. Okay, so f of negative x was negative x cubed. Okay, now I have to find f of x, make the whole thing negative. Are these two things equal? Yes, they are. So I would conclude, yes, this is an odd function. Okay, and that's how I do the comparison every time. I mean, this is an easy one, because that's what x cubed looks like, right? So I already know that's an odd function. But when you look at something like number 2, you kind of see that and you think, well, that kind of looks like an odd function as well. So is that going to be an odd function? Okay, so first thing I do, I find f of negative x. Okay, then I have to compare. So then I'm really setting up and going, is it even? So is f of negative x equal to f of positive x? Is it odd? Is f of negative x the negative of f of x? Okay, so I write out each of these in terms of this function. Okay, f of negative x was negative x cubed plus 1. Is that equal to x cubed plus 1? No, not even. What about odd? So is f of negative x equal to the negative of f of x? Well, be careful here, because actually these two things are not equal. Okay, because here I have a positive sign, here I have a negative sign. So it's actually not even or odd. So this function is actually neither. And the reason why is because that's a cubic function, but it's shifted up. So actually that affects the symmetry, so it's no longer symmetric because of that vertical shift. Okay, something like number 3. So it's the same thing every time. So I start by finding f of negative x. Okay, negative to the 4th power turns positive. Okay, what about absolute value? So look, absolute value of negative 2 is 2. That's the same as absolute value of positive 2. Absolute value of negative 3 is 3. That's the same as absolute value of 3. In other words, absolute value of negative x is the same as absolute value of positive x. Okay, so there's my first step, finding f of negative x. Now I have to do my comparisons. Okay, so I'm asking, is it even? So So for this to be even, f of negative x has to be equal to f of positive x. So in other words, x to the fourth plus absolute value of x has to be equal to x to the fourth plus, oh, look at that. It is even. Okay, if I was to try odd, then I'm asking, is f of negative x the opposite of f of x? Well, f of negative x was that. The negative of f of x would be this. So we'd be asking, are these two quantities the same? Okay, obviously not, right? No. Okay, so indeed, this guy is an even function. Okay, a couple more here. So what about this polynomial function? Okay, f of negative x. Okay, stays negative with the odd power. Okay, now I compare. Okay, f of negative x. That's what I just found. F of x. These are not the same, huh? Okay, what about odd? That's this quantity. Okay, is that equal to the negative of the original function? Let's distribute that negative. Okay, it looks like those are the same. So indeed, this is an odd function. Okay, and the last one. Okay, what is my f of negative x? Okay, and then to compare, so this part will be more interesting. Okay, so is this equal to this? No, okay. Okay, what about odd? Okay, here's my f of negative x. Is that equal to the negative of f of x? Okay, so the question is, are these two things equal? Well, the thing is, look at this right side. I don't know, think about a simple fraction. Remember, if I have something like -2/5, I can write that three ways, with the negative in the front, the negative in the top, or the negative in the bottom. So the question is, I mean, if I take this expression, I guess I can write it three ways. I can write it the way I have it written. I can put the negative in the top, or I can put the negative in the bottom. Okay, so are any of those the same as this? No, not quite, okay? So in none of the three ways I can write the right-hand side actually give me the left-hand side. So that means, again, I would conclude that this guy is neither, okay? It's not even nor odd, so this would be neither.